6.1 has to do with confidence intervals for the mean, and this is for large samples. So anything n is greater than or equal to 30, we will be using this formula and this calculator code when we get there. The objectives: how to find a point estimate. The point estimate here in 6.1 is just x bar. And then how to find the margin of error, okay? Once you have the point estimate and your margin of error, we can find the lower and the upper bound. To find the lower bound, we would just take the point estimate, subtract the margin of error. To find the upper bound, we would take the point estimate and add the margin of error. And then you will also learn how to determine the minimum sample size required when estimating mu. So you're actually going to be solving for n with algebra. Okay, next. All right, we have some definitions here. We have a point estimate. This is a single value that is used to estimate the value of a population parameter. Today, in 6.1, our point estimate is going to be x bar. And then we are going to be able to find an interval estimate. That's a range of values that is used to estimate the value of the population parameter. All right, so today we are actually going to use x bar and your margin of error to estimate the population parameter, in this case, which would be mu. Our confidence interval are just two values. We have a lower and an upper bound. Again, the lower bound is just going to be x bar minus the margin of error. Your upper bound is going to be x bar plus your margin of error. All right. When we're doing this, let me just move this a little bit like this, you are going to be estimating this interval with a certain level of confidence. The confidence level C gives you the overall success rate of the method for calculating the confidence interval. That is C%, so maybe 95% of all possible samples, the method would yield an interval that would capture that true parameter value, okay? The most common levels of confidence we use are 90%, 95%, and 99%. But you can do anything you want. I mean, you could be 87% confidence that a certain interval contains the population parameter. But these are the main ones. Okay. All right. After you find each confidence interval, you are going to be asked to interpret, okay? So I'm going to give you a sentence frame that is going to allow you to be able to interpret every confidence interval you find. All right, here is the sentence frame. We interpret a blank, usually 95, 90, 90%, 99% confidence interval for an unknown parameter, okay? What you want to say is that we are 95% confident that the interval from, this is your lower bound, to your upper bound captures the actual value of the population parameter in whatever context we're talking about. So this right here is your sentence frame to interpret a confidence interval. Example, it was recently reported that Obama's job approval is 52%. This was reported as being 95% or being a 95% confident level with a 3% margin of error. Construct and interpret the interval for the true proportion. Well, the point estimate here is actually 52%. That's really a p-hat or a proportion. In 6.1, we're really working with means. 6.3, we're going to be working with proportions, but we can do the same thing. We want to take the point estimate and subtract the margin of error. Okay, when we do 52 minus 3, we're getting 49. And then to find the upper bound of the confidence interval, we do the point estimate, 52, plus 3 to get 55%. And then we just put these two numbers of your confidence interval into your sentence frame. So now we can say we are 95% confident that the interval from 49% to 55% captures the true, actual, and this is a proportion of people who approve Obama's job performance. When we actually do today 6.1, instead of a proportion, we're going to say mean. Same with 6.2. And then in 6.3 is really when you're going to put proportion into your interpretation. Okay, next we need to know how to find this margin of error. All right, well, we're always going to find it by multiplying a critical value times the standard deviation of the statistic. This is just a general formula that we can use for all margin of errors. Well, how do we find this critical value? Well, it's going to depend on the confidence level. Okay, so again, our most popular confidence levels are 90%, 95%, and 99%. And so there are actually different Z critical values that go with each of these. All right, for example, 90%, the Z critical value would be 1.645. 95% would be 1.96. 99% is 2.575. These can be found on page 305 in your book. These are the most common ones, but again, you can find the critical value for any level of confidence. We could be 59% confident. In a minute, I'm going to show you actually how you would find these values. A greater confidence requires a larger critical value. And then the standard deviation of the statistic depends on the sample size n. All right, and that's what you've been learning in chapter 5 now. When we do an SRS, and we're going to be doing that forever now, or a sampling distribution, what's going to happen is you need to take the standard deviation that they give you and divide it by the square root n. That should look familiar from chapter 5. Okay, starting over again, finding the critical values. We are going to find the main critical values for the most popular confidence intervals, 90%, 95%, and 99%. We're first going to draw the standard normal distribution, and I've done that actually 3 times here. Next, the second step is to label the confidence level in the middle of the curve. All right, so let's just work with 90% first. I have labeled 90% here as a decimal. Well, we know the whole density curve has to add up to 1. So I know that I'm missing 0.10, and I know that the density curve is symmetrical. So I know that each tail is going to be 0.10 divided by 2. So that's going to equal 0.05. Okay, and then same here, 0.05. So that's the area in the table. All right, that's step 3. Now we're going to use your normal table, your Z-chart. All right, your normal table is just your Z-chart. All right, or your calculator to find the Z critical value. You're going to actually get a positive and a negative Z critical value. All right, well, remember when we use our calculator, in order to go from a Z-score, or from an area to a Z-score, we need to use inverse norm. All right, and that's actually looking for the area to the left. So we can always just use this area to the left. I'm going to put 0.05 here. Well, this is a standard normal curve, so your mu is going to be 0 and your sigma is going to be 1. All right. If you were using your chart, you would look in the middle of your chart for the closest to 0.05 and find the corresponding z value. I'm going to use the calculator here. To get to inverse norm, again, we go to menu, probability, distributions, and then inverse norm here. It's going to ask again for the area, that's 0.05. It asks for mu 0, sigma 1, and I'm going to press OK. And this is our z-score. So I'm going to round this to negative 1.645. Well, if that's your negative z-score, guess what your this z-score is over here? Well, that's just positive 1.645. So really, we like to write our z critical value as the positive. So I will say that anytime it's asking me to be 90% confident, the z critical value is 1.645. Might be helpful to write that on a sticky note or something so that you always have it. All right, now we just need to do 95% and 99%. Well, I need to know the area of both of these tails. Well, that's going to be 0.05. That's because 0.95 plus 0.05 adds up to 1. I'm going to divide that by 2, and when I do, I get 0.025. So I know the area in both of these tails is 0.025. That's what I'm going to put into my inverse norm calculator code. So my area is going to be 0.025. My mu again is 0 and sigma is 1. So let's go ahead and do that. So I'm going menu, probability, distributions, inverse normal. My area is 0.025. Mu is 0, sigma is 1. I press OK, and I get negative 1.959. I'm going to round that to negative 1.96. So that's my negative z value. My positive then would be 1.96. We like to put our z critical values as a positive, so that's going to be 1.96. Anytime you use 95%, again, you would use the z critical value of 1.96. Over here, I'm not going to go through all the steps, but the tails in both of these would be 0.01 divided by 2. That would be 0.005. I would then enter this into my calculator. My area would be 0.005. Mu is 0 and sigma is 1. When I do that here, I get negative 2.575. So the positive z-score would be 2.575. So we like to use the positive for our critical value. So our z critical value when we want to be 99% confident is 2.575. I would write all three of these down on a sticky note because you will be using them a lot. All right, next, sorry, my table is so sticky. Whoop, and there's a bug. Okay. All right, confidence intervals for the mean, large samples. That's what we're doing today. Well, I need you to remember this rule in your head forever. When n is greater than or equal to 30, we can basically say that the distribution is normal because it's such a high sample size, and you're able to use your z chart, all right? Well, how do we find the confidence interval for a large mean? Well, what we do is we have to do the point estimate plus or minus the z critical value. Remember, this depends on the level of confidence, depends on confidence level, okay? And then we multiply it by the standard deviation. We multiply it, the standard deviation divided by the square root n, because that is our sampling standard deviation.